Kia ora and welcome back. In this video we're going to discuss Cayleys theorem. Now Cayleys theorem is a very important theorem because it means that the foundation that the early group theorists used, building on groups basically as groups of permutations rather than on the modern approach that we use, such as axioms, was actually the correct one, because Cayleys theorem tells us that actually every group is isomorphic to a permutation group. So in some sense, permutation groups are actually the only groups. Everything else is isomorphic to some kind of group of permutations. So that's quite big. So we're going to state and prove Cayley's theorem in this one, and then we're going to look at some properties of isomorphisms that hold true for all isomorphisms. Right, so here's the theorem, and it's a very easy one to state. It simply says that every group is isomorphic to a group of permutations. Now, this is not, on the face of it, an easy thing to think about how to prove, because remember, to show that a group is isomorphic to another group, we need to come up with some kind of permutation, some kind of isomorphism mapping that we can show as an isomorphism. So here, we don't have any information about the groups in question, so we're going to need to define the group of permutations, we're going to need to define the isomorphism mapping, and then we're going to have to show that that all sort of fits together. So we can't just pull these out of thin air, we're going to have to state what they are. So we'll start our proof off by just saying let G be any group. Alright, and I'm also going to define the group of permutations that we're going to eventually end up proving as isomorphic to G, because again, we can't just pluck this one out of thin air. It's a little bit tricky to do that. So this is something that I'm actually giving you, it's not something we're deriving here. So we need a permutation group. And we'll define one as follows. So for any G, so for any member of our group G, we'll define a mapping, which I'll call T subscript G, which maps G onto itself to be Tg of x is just equal to G times x for all x in our group. Alright, now this element here, this is in fact a permutation. On G. Okay, I'm not going to prove this here because remember it's just going to take a little bit of extra space to do that. But remember, a permutation is simply a function from a set onto itself that's one-to-one and onto. It's how we defined permutations at the beginning of our permutation group section. Don't get distracted by the fact that we then subsequently introduced notation that we've used ever since with permutations. By definition, a permutation is just a one-to-one and onto map of a set onto itself. So Tg is pretty easy to show as a permutation on the elements of G. Okay, so we're going to therefore build our permutation group to just be the set of all of these permutations, with the group operation being composition of these permutations. So I'll say let G bar equal the set of all the TGs where G is an element of G. And G bar forms a group under function composition. Okay, so let's just see how that works. For G and H in our group G, we see that TG TH of x is equal to TG of TH of x, which equals G times HX. Well, I should do it in two steps, shall we? TG of HX, which equals G times HX, which then equals TGH of x. Okay, so that's how we compose members in this permutation group together. We just multiply their subscripts. The identity, TE is the identity and the inverse of an element Tg is just equal to Tg inverse. Okay, and we know that function composition is associative. And so G bar forms a group. Okay, so just sort of blatted through our test for groups. We've shown that it's closed, our operation is closed. When we multiply them together, we get this one here. So our operation is a binary operation on this set. TE is quite clearly the identity, and TG inverse is TG inverse. Likewise, we have associativity built in because function composition is always associative. Therefore, the G bar that I've set up is definitely a group under function composition. So let's just take a step back and see what we now have. We have a group, G, and we have a group of permutations, G bar. Our next job is to show that they are isomorphic to each other. Now this one's pretty straightforward at this point in time. We've done the sort of hard bit of just setting these things up. Need to show that they're isomorphic. That G is isomorphic to G bar. Alright, so that means we need a mapping phi that we can test whether or not it's as to whether or not it's an isomorphism. So define. Now we'll define phi the completely obvious way. Phi maps G to G bar by phi of G simply equals Tg. Okay, so we now need to show that it's one-to-one and onto. So one-to-one. Assume that phi of G equals phi of H, i.e. that Tg equals Th. Now, it kind of is hard to see what to do here because we would just want to show somehow that G has got to be equal to H. The easiest way to do this is just to choose any element and map it through the permutation. So we'll choose an element of G, e.g. the identity, and hence if these two permutations are equal, they should certainly be equal when applied to their element E is equal to Th of E, which if we just apply the definition of Tg and Th now, Ge equals He, i.e. G is equal to H. Alright, so our mapping is one-to-one. We've shown that the subscripts G and H must be equal. We had to pluck out a particular element here to turn the statement about permutations themselves into a statement about elements of G, but that didn't prove to be too hard. Now again, this mapping is onto by construction. Okay, you can see that no matter what element Tg you choose out of that, out of our group G bar here, the corresponding element of G is just the subscript Tg, so I don't have to do anything to prove the onto-ness of this. And finally, I've got to choose that show that it's operation preserving. So now I have phi of AB is equal to T AB by definition, but we've established already that TAB, let's just look at this equation over here, TAB is actually just the composition of the two, is equal to TA TB, and therefore that's equal to phi of A, phi of B. Okay, hence phi is an isomorphism and G is therefore isomorphic to G bar. And just one little note, G bar has a name. It's called the left regular representation of G. Of G. Alright, so let's just do this, build this permutation group for a particular example, just so we can see that it actually kind of makes sense, because it's all a bit abstract at the moment. So we're going to do it for U of 12. We're going to form the left regular representation of U of 12 and just see what all these pieces look like with an actual group that we know. Right, so U of 12. We know the elements of U of 12. We've come across this quite a few times now. All the numbers relatively prime to 12, which are 1, 5, 7, and 11. So to construct the left regular representation, we need to build the 4 permutations, which are going to be T1, T5, T7, and T11. So T1 is just the permutation that multiplies everything in the group by 1 mod 12. So that gives me 1, 5, 7, and 11. T5 is the permutation that multiplies everything in the group by 5. So it'll be 5. 5 5s are 25, which is 1 mod 12. 5 7s are 35, which is 11 mod 12. And 5 11s are 55, which is 7 mod 12. Likewise, T7 is the permutation that multiplies everything in U of 12 by 7. So 7 1s are 7, 7 5s are 35, which is 11. 7 7s are 49, which is 1. And 7 11s are 77, which is 5 more than 72, so that's 5. Finally, we'll do the same exercise for 11. 1, 5, 7, 11. 11 1s are 11. 11 5s are 55, which boils down to being 7. 11 7s are 77, which as we said before was 5. And finally, we get 11 11s are 121, which is 1 more than 120, which is a multiple of 12, so that's 1. Okay, so these are the 4 permutations that form the left regular representation of U of 12. And if we were to build the Cayley tables of these two groups, so let's do the U of 12 one again. We get the familiar Cayley table here, and then we can build the same Cayley table for U bar of 12, and the elements are now going to be T1, T5, T7, and T11. So if I compose these together, my composition just works by multiplying together the indices, so you can see quite clearly that I'm just going to get exactly the same structure of Cayley table here. And we can see that these Cayley tables are exactly the same. The only difference is the capital T's that are on each entry. They have exactly the same structure, and you can see that my mapping phi maps 1 to T1 and 5 to T5, etc. And so we most definitely have an isomorphism between the two. So that's how it works. You can see that my U bar is a group of permutations. Here are the 4 permutations in question. They are genuine permutations, exactly what we are more familiar with them being. And building the Cayley tables show they come out to be exactly the same type of structure. Okay, so we're going to finish off this video by stating a bunch of properties of isomorphisms, just so we know what it is we can test when we're trying to see whether or not two groups are isomorphic. Right, so our first theorem is properties of isomorphisms that act on elements. So for the following list of properties that I'm going to give you, this is theorem 6.2 in Galilean, by the way. Phi is an isomorphism that takes G onto G bar. So the first property is that phi maps the identity of G onto the identity of G bar. So that always has to happen. Second property says that phi of A to the power of n is equal to phi of A all to the power of n. Now this is just a simple consequence of operation preservation being carried out a number of times in succession. Next property is a property about when two elements commute. So if A and B commute in G, this is exactly equivalent to whether or not phi of A and phi of B commute in G bar. Okay, the fourth one applies to cyclic groups, and it says that if we have a cyclic group G generated by A, then that means that G bar is also cyclic, and it is generated by phi of A. Okay, in a similar vein, the order of A is equal to the order of phi of A. Element orders are the same on both sides of an isomorphism. Pretty much anything we come up with is going to be the same on both sides. Okay, so to do with equations, x to the k equals b has the same number of solutions as x to the k equals phi of b. In G bar. Alright, continue on, one more. If G is finite, then G and G bar have exactly the same number of elements of each order. Okay, and that completes our list. So these properties basically are things that we can test. If we've got two groups, and especially if we're trying to establish that two groups are not isomorphic, if any of these properties are violated, for example, you find one group has an element of order 5 and the other one doesn't, then that's enough to tell you that the groups are not isomorphic. So these properties have to hold true for all groups and all elements, and yeah, like I said, they're useful tools in establishing whether or not two groups are isomorphic. Okay, I'm not going to prove this, so I'll just refer you to Gallian for the proof for these. None of them are all that tricky, but they're worth reading. Alright, now similarly we have sort of this is the element level. Everything here is involving individual elements of a group. We have properties of isomorphisms acting on groups as well, and that's theorem 6.3. Okay, so our first property at a group level is that if we have phi being an isomorphism, from G to G bar, then phi inverse is likewise an isomorphism, this time from G bar to G. Our next one says that if one group is abelian, then so must be the other. Okay, so if G is abelian, then that means G bar must be abelian, and vice versa. Similarly, same thing applies to cyclic groups. We kind of said that already. So if G is cyclic, then it follows that G bar must also be cyclic, and generators map to each other as well. Okay, next one applies to subgroups. So if K is a subgroup of G, then phi of K, now whenever I apply a mapping to a whole set, it's just the mapping of individual elements all collected up. So that's the set of phi of little k's, where K are members of the big K, must be a subgroup of G bar. Okay, so subgroups map to subgroups. Number 5. Likewise, same thing applies in reverse. If K bar is a subgroup of G bar, then it follows that the inverse map of K bar, defined the same way, is a subgroup of G. And finally, we'll make a statement about the centers, that phi of the center of our group is simply equal to the center of G bar. Okay, so these are some sort of like bigger picture group level perspective properties that must always be true. Things like cyclic groups must be isomorphic to other cyclic groups and all that kind of thing. Subgroups must follow through. So if anything differs between two groups, like orders of subgroups and all that kind of thing, then you automatically don't have an isomorphism. So this whole collection of properties is just worth having available as reference when you're trying to establish whether or not two things are isomorphic or what that means. So again, I'm not going to state the proofs to these in this video because it will just get too long, but I'll refer you to Gallian for the proofs of both of these theorems. That's enough for this video, so we'll catch you next time. Have a good one.